First, there is nothing. No time, no space, not even emptiness, for there is no space to be empty. Then from this void explodes a universe far smaller than the tiniest speck of dust, and from this speck of dust, this infinite darkness will emerge all of creation. Prior to this moment, when the universe began, there was nothing. During and after the moment, there was something. Our universe. The Big Bang Theory explains what happened during and after that moment. Lemaitre and Gamow proposed this theory in 1927. According to the theory, at the beginning of the universe, the whole matter of the universe was one concentrated and extremely dense and hot fireball. Then about 20 billion years ago, a vast explosion occurred. The matter was broken into pieces, which were thrown out in high speed in all directions, forming stars and galaxies, which are still moving away from one another. But the question lies, how do we know this theory is true? Well, today we're bringing you 3 theories of evidence on why the Big Bang has happened billions of years ago.
In 1965, Erno Penzias and Robert Wilson of Bell Laboratories observed the radio sky at the wavelength of 10 centimeters with a high signal-to-noise and made a discovery for which they won a Nobel Prize. Anywhere they pointed their telescopes there were always a uniform level of radiation that filled all of space. This is unknown cosmic microwave background radiation. Till the 1960s, most scientists believed in the steady-state theory. This was the idea that the galaxies were being pushed apart by matter leaking into the universe through holes. The cosmic microwave background, CMB, is thought to be leftover radiation from the Big Bang, or the time when the universe began. As the theory goes, when the universe was born and underwent a rapid inflation and expansion, the universe is still expanding today. The expansion rate appears different depending on where you look. The CMB represents the heat left over from the Big Bang. You can't see the CMB with your naked eye, but it is everywhere in the universe. It is invisible to humans because it's so cold, just 2.725 degrees above absolute zero, minus 459.67 degrees Fahrenheit, or minus 273.15 degrees Celsius. This means its radiation is most visible to the microwave part of the electromagnetic spectrum. About 380,000 years after the Big Bang, the universe was cool enough that hydrogen could form. Because of the CMB, photons are barely affected by hitting hydrogen, and the photons travel in straight lines. Cosmologists refer to the surface as last scattering, when the CMB photons last hit matter. After that, the universe was too big. So when we map the CMB, we are looking back in time to 380,000 years after the Big Bang, and just after the universe was a peg to radiation. CMB radiation tells us the age of composition of the universe and raises new questions that must be answered. Cosmic microwave background, CMB, is radiation that fills the universe and can be detected in every direction. Microwaves are invisible to the naked eye, so they cannot be seen without interference. The discovery of CMB is regarded as one of the most foremost cosmological, indeed next to the discovery of the expanding universe by Hubble and that of Planck's constant by Max Planck.
Element formation of the early universe is called the Big Bang
Nucleosynthesis.
The predicted abundance of deuterium, helium, and lithium depends on the density of ordinary matter in the early universe, as shown in figure at left. Hydrogen is the most abundant element in the universe. Helium is second. However, after this, the rank of abundance does not continue to correspond to the atomic number. Oxygen has abundance ranked 3, but atomic number 8. All others are substantially less common. Elements formed in these stages range from oxygen through iron. During a supernova, the star releases very large amounts of energy, as well as neutrons, which allows elements heavier than iron, such as uranium and gold, to be produced. In the supernova of all these elements are expelled out into space. Hydrogen and helium. Hydrogen is an element, usually in the form of gas, that consists of one proton and one electron. Hydrogen is the most abundant element in the universe, accounting for about 75% of its normal matter, and it was created for the Big Bang. This is a second key prediction of the Big Bang. The universe was, before any stars formed, made up about 75% hydrogen and 25% helium, and much less than 1% of all other elements combined. How does the Big Bang predict this, and how do we observe it? Well, remember we said the universe was hot and dense in the past. At some point, it was so hot that the neutral atoms couldn't form because high energy photons would just come and kick electrons off the nuclei like this. So you work through the math, and when the universe finally cools down enough that you can form stable, determine 1 proton plus 1 neutron equals 1 deuteron. There's only about 1 neutron for every 7 protons. The exact number depends on how many protons there are. Then all of the neutrons starts to fuse together and go through the reactions like this. People used to argue that it could all start out as hydrogen, and you can make as much helium as you want in stars, but that part is true. But you also make a lot of heavier elements like carbon, oxygen, and nitrogen, and sometimes silicon, neon, and sometimes even iron, cobalt, and nickel. And when you get a supernova, you can make anything all the way up to uranium. When we look at coronal gas clouds, we see less than 1% of everything besides hydrogen and helium. So that is a real tough challenge for theories that are the Big Bang.
After we look at a C and B, cosmic microwave background, and the abundance of light in the universe, now we look at part 3, the expansion of the universe. If you're deep in a gravitational field, like close to a black hole, you have to use up energy to climb out of it. For light of all types, energy and wavelength are very closely related to each other. Smaller wavelength equals higher energy, and larger wavelength equals lower energy. So if you need to climb out of a strong gravitational field, you'll lose energy, and therefore your light gets shifted towards the red. This is what we call a redshift, where something happens to make the wavelength of your light longer and lower in energy. But gravitational redshift is rarely significant. 2 other effects are far more important. If an object that emits light moves away from you, the light from it gets redshifted. This is the same exact effect. The Doppler effect, better known as the Doppler shift. This is what causes police sirens to sound lower pitched when they move away from you. If a light-emitting object moves toward you, the light gets blue shifted and becomes more energetic. Although this is incredibly useful, this is not what's happening to the light in the universe. Remember, I told you that these distant galaxies aren't moving. The space between them is just expanding. Well, guess what? The expanding space causes a redshift. As you can see, space expands as the wavelengths of light also expand, as you can see. It is literally millions and millions of these individual measurements that we've been able to determine the entire history of how the universe expanded. That, among other things, is how we discovered dark energy in the accelerating universe. Pretty remarkable stuff, and yet not intuitive at all. So what should you take away from this? That as light travels through space and space expands, it causes the wavelength of that very light to expand too, and that's how we learn about the cosmic expansion of our universe. Again, it's expansion that causes the redshift and not motion. Hope this helps shed some light on most of the confusing stuff.